Welcome to Module 201C on Principles of AC Circuits. This module has two different objectives that we're going to split into two videos. The first video is going to be on the three current limiting circuit properties that we find in an AC circuit, and the second video is going to be on other things that we need to think about that could affect total circuit resistance. We're going to discuss a little bit more about the three properties that oppose current in their own way in an AC circuit, being resistance, inductance, and capacitance. Resistance is the physical opposition to current flow. And what that means is, depending on the type of materials that we use inside our circuits, some of them will have a greater opposition to the movement of electrons than other ones. And each different type of material has a different resistive value based on its ability to move electrons. Copper has a very low resistance, which is why we use that as our conductor, whereas nylon would have a very high resistance, which is why we would use that as an insulator. Depending on the level of resistance of the physical property of that material would also depend on the current flow inside that circuit. The higher the resistance, the lower the total current is going to be. Inductance opposes a change in current, and inductance can exist in both an AC and a DC circuit. However, in a DC circuit, that opposition only lasts while the current changes, which is only for a fraction of a second. Then we have a stable current, therefore we have no more inductance. In an AC circuit, I have a constantly changing current value. As I rise from zero to peak and then back down to zero and then negative values and back up to zero again, there's always a difference in my current. Therefore, there's always an opposition to that current change as well. Inductance will create what's called a counter EMF inside the coil, and that counter EMF will also create a counter current flow. That opposing current is also dependent on the magnitude and direction of the magnetic field. As my current is changing, that magnetic field is also changing not only in magnitude, but as we pass a peak, that magnetic field also changes in direction. And this is how inductance always creates an opposition to the changing current flow. If you consider when my current of my circuit starts at zero and goes up towards peak, the opposing current would have a negative value. Therefore, it's taking away from that rise in current. So it's always opposing the current as it goes up towards the peak. However, as it passes the peak, the magnetic field changes direction and my induced current now changes polarity. Now I have a positive, therefore it helps with my falling current. So it slows down the fall of the current because now it's adding to that current. As my current value passes the zero line and turns into a negative value, my induced current is still positive. So it slows down the rise up to the peak negative value because it's adding positive current to it. As it passed my negative peak, now I've changed magnetic direction again, which means now my induced current is going to be a negative value, and it's going to slow down the fall towards zero again. As my sine wave changes, my magnetic field changes, my induced current changes, therefore I'm always giving an opposition to that change in current. The opposition that inductance creates with the counter EMF is called inductive reactance. It is measured in ohms and represented by the letters XL. When it comes to capacitors, their job is to hold a voltage or to hold a charge value. And they have a property called capacitance. In a DC circuit, that capacitance is charged fully and then it stops charging. Therefore, my capacitance goes away when the charging stops. However, in my AC circuit, since my voltage is constantly changing, it also means that that capacitor is constantly charging and discharging. Keep in mind that as I start at zero and I start increasing my voltage, my system is charging the capacitor as at the same time it's building that voltage. And then when I pass the peak and start to lower my voltage, my capacitor is fully charged and it's going to start to discharge back into the system again. And this is how capacitance is offsetting that change in voltage. As my voltage starts at zero and rises to a peak value, that's when my capacitor is charging. And as I reach that peak, my capacitor is also fully charged. As I pass the peak and I start to lower my voltage, the capacitor is discharging into the circuit, therefore helping that voltage along a little bit further. As my voltage changes, my capacitor is always opposing the change either by discharging or charging at the same time as I'm either rising or lowering my voltage value. As capacitance opposes voltage, it also results in a lower overall amperage, since if I have less voltage, I will have less amperage according to Ohm's law. This is called capacitive reactance. It is measured in ohms and is represented by Xc. In my circuit, I now have three different ways to oppose current: through resistance, through inductive reactance, and through capacitive reactance. Inductive reactance and capacitive reactance combine in order to just create the term reactance, represented by X. And it is really the integration between resistance and reactance that create what is called impedance. Impedance is the total value of opposition I can have in my AC circuit, and it is going to include every single type of possible opposition I can have. The impedance now is what I would refer to when I'm trying to figure out my current in my circuit. So Ohm's law would include impedance instead of resistance inside an AC circuit. This is the end of part 1 of 201C. Go back to Blackboard and complete the knowledge check, and then you can continue on to part 2.